so in section 4.2, we're going to start talking about a concept called logarithms. I don't expect you to be as comfortable and confident with logarithms as you were with exponents, but I will say the better you understand exponents, the easier logarithms are to make the jump to, okay? So before I show you what a logarithm is, let's remind ourselves what an inverse was. This is all the way back on test 1. Inverses are, remember, opposite functions that undo each other. The other thing about inverses, remember, is that x and y are swapped. So all the x's become y's, all the y's become x's. So here is an exponential function that we just got finished looking at, y equals b to the x power. Okay, so this was the same type of function we discussed in 4.1. So what if I asked you to find the inverse of that guy? Okay, what did I say we do with x and y if we want the inverse? We flip them, right? So the inverse would be x equals b to the y power. Okay, so think of this like this is the inverse of an exponential function. But the problem with this is normally when we did inverses before, remember we would then solve for y. What's going to be the problem with us trying to solve for y here? Where's y located at? In the exponent, and that's kind of at an untouchable location as it is. And so we're going to look at a new form for the inverse called the logarithm. Okay, so it's going to be the same as saying y equals log base b of x. Make sure when you write it that the b is tiny. Like b should be like exponent size. So this is what we call a logarithmic function. But that's just a fancy way to say a logarithm. So once you learn that logarithms are just fancy exponents, I promise this is not going to be too difficult, but until you can get as comfortable, or at least maybe half as comfortable with logarithms as you are with exponents, they're going to seem a little strange. So logarithms are simply just another way to write the inverse of an exponential function. They're also the way that we, quote, undo exponential functions. So remember how addition and subtraction undo each other, how multiplication and division undo each other. Well, logarithms are going to undo exponents. Okay. So I just want us to kind of get our feet wet with kind of what goes where. Okay. So before I talk about this, notice that the base here, so before you write anything else, right, the base here becomes the base over here, right? Notice that the exponent here becomes the answer here, right? And then the x value here becomes what we're taking the log of here. So you really just have like 3 numbers / letters, and you have to know where they go, right? So let's practice that kind of back and forth. So first, I want you to take a log form problem and switch it back to exponential form, and then maybe we'll do the other way too. So here is a logarithmic expression that is something that's true, that works out. So I don't think there's any shocker here, right? This is logarithmic form. So you just need to learn what goes where. Okay, so we're going to rewrite this to be what we're more comfortable with, right? And there's no question that we're more comfortable with exponents, right? So notice the order that I'm about to write these. Okay, so the base becomes the base. Notice the base of the logarithm is now the base of the exponent. Okay, the answer to the logarithm is always the exponent in exponential form. and then the other number goes here. Notice that's the only way these numbers combine and make it true, right? 2 to the third power is actually 8. 2 times 2 times 2. 2 times itself 3 times. So this would be exponential form. So if you kind of know what things are called, I think you get the base for free because the base here becomes the base over here. So it's really just knowing where the other two things go, right? And once you figure the second thing, frankly, it's just kind of by default where the third one would need to go. All right, so let's see if we can go backwards. So let's say I'm going to give you something in exponential form and I want you to write it in logarithmic form. So before you even try to tackle the homework, you need to pay really close attention to these first two examples we're doing today to make sure you know kind of what goes where, because it's kind of like a puzzle. So notice, no surprise, right? 4 squared is 16, right? That's true. 4 times 4 is 16. Okay, so this is, of course, what kind of form? This is exponential form. So I'm asking you to rewrite this in a different form, but put things where they go, right? So I'm going to do the easy part. It is going to be the log base 4, because the base here is 4, so the base of a log becomes 4. And then do y'all remember what to do now? Where's the exponent supposed to go in a logarithm? I'm going to skip some space. It's supposed to be the answer, right? And so then by default, the 16 has to go here. Okay, so notice the 4 is pretty obvious. It's just the 16 and the 2, you have to figure out which format they go in. And so if you've never really covered logarithms before, that's okay. You just need to kind of quickly learn where things go, essentially. But what that rewrite step, once you get the hang of it, allows for you to do is take things that are maybe in an uncomfortable form and try to rewrite it. So let's say I asked you to solve the log base 5 of x equals 2. So I would look at that and I would be like, I don't really prefer this logarithm form, so I'm going to immediately change it to the form I'm more comfortable with, which is what? Exponential form. All I have to do is figure out what goes where. Okay, so I'm going to do the one that's easy. The 5 base becomes the 5 base of the exponent. Okay. What happens to the answer to the logarithm? Where do we put that when we switch it to exponential form? So the 2 becomes the what? The 2 becomes the exponent. Sorry, I'm kind of giving you the answer already. And then the x value just goes in the other spot. So we should be able to solve this now, right? Because what is 5 squared, of course? 25. So we're going to take a break and look at some rules, but here is something that I probably will have you write down more than once. The answer to a logarithmic expression or a logarithm problem, if you want to say it like that, is basically what exponent you need to raise the base to get the other number. So the answer to a logarithmic expression is always looking for the exponent. Okay, it's asking you what power do I need to raise that base to give me the answer that I'm looking for. Notice that's what it was here, right? What power was I raising the 5 to? I was raising it to the 2 power because that was the answer to the logarithmic expression. Okay, so we are going to review a little bit further the rules of exponents that I just mentioned, but we're going to do it with some examples. So we already kind of wrote this today, so I'm going to write it briefly, but I really want to get to some examples. So remember, the product rule said, I'm going to write it a little bit differently than what I had before. X to the a power times x to the b power would be x to the a plus b power. So notice before I think I listed them as b for base, but this time I'm listing them as x's. Same difference, same rule. So here's the gist of the rule. When multiplying terms with exponents, add the exponents. I don't want to get really wordy with this. The bases do have to be the same. So that's kind of a given. So when multiplying terms with exponents, as long as it has the same base, you're going to add the exponents. So let's look at some examples with maybe some varied difficulty. So we're used to problems like this before now, where I say combine x to the third times x to the fifth. So what would that obviously be? X to the eighth, right? So we would add the 5 plus the 3, and we would get x to the eighth. But that same rule applies if you have an exponential function, or maybe something where you have a base other than x. So notice this is 3 to the 7th times 3 to the 8th. It's the same exact rule as I had before. Okay. Notice what we are not going to do is do 3 times 3, because we're not supposed to do multiplication until we handle what part first? Exponents first, right? So notice the base isn't going to change. All we're going to do is do what with the exponents? Add them. Okay, I'm not going to punch that in my calculator, by the way, because that would be a really crazy big number, because that would be 3 times itself how many times? 15 times, right? So that would just be super, super large. But even if you have, I'm going to put a star by this one, even if you have something weird, like 2 to the x power times 2 to the 3x power, the power or product rule, still applies here. Notice the bases are still the same. So what are you supposed to do with those exponents, just like you did for the previous 2 examples? Just add them. So this would be 2 to the x plus 3x power. And what is x plus another 3x? 1x plus 3x would be how many? 4x. Okay. So notice we're taking old rules and just applying them to new types of problems. All right, so let's look a little further at the quotient rule. So I know we already briefly talked about that too, back in the exponential section. So remember this, what did we do with the exponents again? Subtract them. So the explanation of this is when dividing terms with exponents, again, make sure the exponents are the bases are the same. But when dividing terms with exponents, you subtract the exponents. So kind of like we did on the first one, let's do some examples of kind of some varied difficulty. So if you have x cubed over x to the fifth, notice the bases are the same, so I'm going to subtract those exponents. So this is going to be x to the 3 minus 5 power, which is x to the negative 2. Okay, if you're still not comfortable with negative exponents, you need to review that, because you're going to need to get more comfortable with them. This is the same as 1 over x squared, and in fact, that's how I would want you to write that answer. I would not want you to leave it as x to the negative 2 power. It's 1 over x to the positive power, whatever it happens to be. Remember, negative exponents create fractions. So what if you had this? So notice instead of x's, now I have numbers for bases, right? But notice that I can still use the quotient rule because the bases are the same. They're both 4. So I'm going to do the same thing that I was doing before. I'm going to keep the base the same, and what am I going to do with the 5 and the 2? Subtract them. So it would just be 4 cubed, which I probably could go ahead and work that one out, right? I didn't do it here because it would have been crazy big, but 4 cubed is not bad, right? 4 times 4 times 4 would be 64. Okay, so when you can write something nicer, we'll try to. But what I want us to be able to transition to is how do you solve weirder ones like this? Okay, so notice definitely still quotient rule, right? We're still dividing. The bases are still the same. So what am I going to do with those exponents just like I have been? The base is going to stay 3, and what am I going to do with the 3x and the 4x? Subtract them, right? Notice it's always top minus bottom. So I end up getting 3 to the negative x power, which is the same as saying 1 over 3 to the x power, because negative exponents create what? Fractions. Okay, we really have to know that. So just like you wouldn't give an answer as 2/4 when you could reduce it to a half, I don't want you to leave an answer with a negative exponent. It's not considered simplified, so I want you to rewrite it as a fraction. And then lastly, we'll talk about this one a little more in depth, the power rule. So this is for when you have a power raised to another power. So what did I tell you to do with the exponents? Multiply them, so just be x to the AB power. So the everyday explanation of this is when raising an exponential term, so it's already an exponent to another power. So it's like something squared or something like that, and then you raise it to a power again. You're going to multiply the exponents. So let's just do a couple examples of this one. So the old school version might look something like this. X cubed, but then to the 4th. So I would do what with those exponents? Multiply them, so it would just be x to the 12th. But also make sure you can handle weirder things, like what if it's 3 to the x power, but then raised to the negative 2 power? So notice it's still an exponent being raised to another exponent. So what do I want you to do with those exponents? Yeah, so I want you to say 3 and then to the x times negative 2. So that's a multiplication dot. But yeah, you're exactly right. It'd be 3 to the negative 2x. So that'd be almost right, but why wouldn't I like you to leave it like this? Because it's a negative exponent, right? So it would be 1 over 3 to the 2x. Okay, so next time we're going to look at some logarithms that use maybe some of these more unusual exponent rules here. So just be ready to kind of continue on with this next time. On with section 4.2 then. So remember last time we started looking at logarithms and what they are. Remember logarithms are just the inverses of exponents, right? So we talked about kind of how to rewrite them in exponential form. So let's just kind of get right to maybe some solving questions where if you know what the logarithm is always asking you for, we should be able to do it. So I'm kind of exaggerating the size of the 16 there because I want to really accentuate that you're supposed to be writing the 4 tiny. The log and the 16 are normal size. Okay, so notice that I'm asking you to find the answer here. Okay, and what did I say the answer to a logarithm in general always was? So the answer to a log is the what? Yes, the exponent you need. So I gave you a longer description last time, but essentially I'm asking you to find the exponent. Okay, so what I'm really asking you for is, what do I need to raise 4 to the power of So what needs to go in the exponent spot so that it gives me an answer of what? 16, okay? And then notice what's the answer, of course? 2. So just to be clear, log base 4 of 16 is 2, but on a test or a quiz or something, I want to see this rewrite statement. So it's 2 because 4 squared is 16, and the answer is the exponent. Okay, so with the same kind of thought process, let's look at some with maybe a little more unusual exponents when all is said and done. So what about log base 7 of 1/7? Okay, so let's talk about what this is asking first thing. Okay, so this is asking, what do I need to raise 7 to the power of to give me 1/7 as an answer? Okay, so we need to think outside the box a little bit, but what kind of exponents give us fractions? So if we don't know that, we definitely need to review that, but what kind of exponents give us fractions? Negatives, okay? So let's just pretend like this were regular 7, right? What power of 7 would you raise, what would you raise 7 to give you 7 as an answer? It'd be first power, right? But because it's 1/7, what will actually be the answer then? Not 1, but what? -1? Okay, so the answer is -1 since 7 to the -1 power equals 1/7. Okay, so maybe you need to rewrite that, but remember that negative exponents indicate that we have fractions. While we're on the concept of weird exponents, remember that fractional exponents give us what kind of things? Like, what does something to the 1/2 power mean? Do we remember that? 1/2 power means square root. Okay, 1/3 power means cube root. So we're going to need to be able to identify these more unusual exponents as well. So let's look at a couple more examples where maybe we're asked to evaluate, and maybe the exponent is not just a positive whole number. So again, not to beat a dead horse, but what's this asking for in general? What are you being asked to find when you're asked to solve a log? You're asked to find the exponent, right? So this is asking you a specific question. This is asking, what do I need to raise 2 to the power of to give me 1/32? Okay, so because it's a fraction, what kind of answer am I going to have as far as the exponent goes? It's going to be negative, right? And so now we just need to figure out like how many 2's we need, right? 2 times 2 is 4, times another 2 is 8, then 16, then 32. So how many would that take then? So 2 times 2, 5 of them, right? So it's not just 5 though, the answer is going to be what? -5, right? But that is since 2 to the -5 equals 1/32. So I want to be clear that we have some work we're showing here, but the answer is just plain old -5. Okay, the answer here is just plain old -1. All right, so what if we do have a root question? So the log base 6 of the cube root of 6. So this looks weird, but it is asking something similar, right? It is asking what? Y'all tell me. What's the question that it's really asking you? So you take the base, right? And what are you being asked to find? 6 to what power gives us the cube root of 6? Okay, so what kind of powers give us roots? We just talked about it. Fractional exponents give us roots, right? And notice it's cube root instead of square root. So what would the fraction actually be for cube root? So if it's 1/2 for square root, what's it for cube root? It's 1/3. So if you're uncomfortable with unusual exponents, you're probably going to need to study those really before we go much further with logarithms. Okay, before you do your homework for this section, I would definitely make sure you understand those more unusual exponents. All right, so one more. And then we're going to talk about some just general rules we can know. So log base 5 of the square root of 5. Okay, so what does this mean? If you're going to rewrite what it's really asking, what does it mean? Yeah, what exponent do you need to raise 5 to give you an answer of square root of 5? Okay, and what's the answer? What exponent gives us square root as opposed to cube root like the last one? So it would just be a half. If it's fourth root, it'll be a fourth. If it's fifth root, it'll be a fifth. Okay, so even, we're going to do a lot of examples today, but that's just because these problems are really, really quick once you figure out what it's asking for. So let's do a really kind of weird one. So what if the base is something like this? Okay, well, we're not going to stress out about how large that base is. We're just going to rewrite it. Okay, so what is this really asking then? What do I need to raise 121 to the power of to give me an answer of 1? Well, there's only one exponent that gives me an answer of 1 always. Okay, do you remember what exponent always gives you an answer of 1? So what power always gives you an answer of 1 no matter what the base is? No, that would be, so 1,021 to the first power would be 1,021, right? So it's not 1. So yeah, 0 power is what always gives you an answer of 1. So the answer here is 0. So that's what we're going to circle. But the answer is 0 since anything to the 0 power, remember, is 1. So that's one of our rules that we really need to know. So notice the 1,021 was kind of unimportant, right? That could have been anything, okay? And in fact, the log base any b at all of 1 is always 0, okay? And this works for any base, because any base to the 0 power will always be 1, okay? So that's a rule that I want you to know, but to be honest, I'd rather you not just straight up memorize it. I'd rather you understand the reason for it, and that's because the exponent that you would raise b to would always give you an answer of 1. It wouldn't matter what b was, because 10 to the 0 power is 1. 1,000 to the 0 power is 1. It doesn't really matter. All right, so that is one of the rules I want you to know, or at least I want you to know how to get it. So here's a demonstration of the next rule I want you to know. Okay, so what do you notice about this log? What do you notice about the two numbers I'm asking you about? The base and the other number are the what? They're the same as each other. Okay, so let's talk about what this is asking. So this means 20 raised to the what power gives me an answer of 20. Okay, so what power always gives you back itself? 1. So this would be 1, and that is since 20 to the first power equals 20. So notice the 20 part is kind of unimportant, right? But the rule is if you're finding the log base b of the same number, in other words, there's a duplicate here and here, you're always going to get an answer of 1 for any b. So do you see why I say I don't really care if you memorize these two rules? I'm putting a star by them. I want you to know them, but as far as memorizing them, as long as you know how to rewrite a log, you really shouldn't have to, quote, memorize them. You should just be able to kind of reason those out. Okay, So let's talk about the log that's on your calculator. I don't know if last time any of you tried to use the calculator, but the natural or the understood base for the LOG button on your calculator, so if you have a TI, the logarithm keys are on this left column right here, okay? Notice there's one that says LOG and one that says natural log, okay? Those are both logarithms. The LOG button on the calculator is in base 10. So if you try to punch a regular, like a log base 3 in the calculator without changing the base, which some of the newer calculators allows you to do, it's not going to give you the answer you expect because it's going to be doing powers of 10. Okay, so when you type in log of 100 on your calculator, it actually means the log base 10, even though you don't specify. So when you use the LOG button on the calculator, it's understood to be base 10. By the way, that's because our number system is base 10. Okay, and what I mean by that is we have nine digits plus 0, right? So we have 10 total digits. And then once you get past 9, you don't come up with a new symbol for 10. You just start rearranging the digits again. So we're going to punch this in the calculator, but I want to talk about what we expect the answer to be, right? What does this mean? So what does log base 10 of 100 really mean? 10 to the what power gives me 100? Okay, so what am I expecting my answer to be then? What power of 10 does give me 100? 2, right? 10 times itself. Okay, so let's go ahead and punch that in the calculator. Let me get out of the glare here. So we punch this in the calculator. Just do log of 100. Okay, and notice it's going to do what we want because it happens to be base 10, so I know it's kind of dark there. But note the answer's 2, just like we thought. Okay, so just to be clear, the understood base, when you're not given one, when it's not written down, the understood base for LOG log is 10. So if you're asked to evaluate a problem and it just says log of 1,000 and it doesn't give you a base, we're going to assume that the base is 10. Okay? Okay, so that's the LOG button on your calculator, but like I mentioned before, we also have another log button, looks like LN. Okay, I usually use like a cursive L for LN, that way it doesn't look like a 1, but a lot of the calculators will have it capitalized, but LN on the calculator is actually called the natural log. And the understood base of it is actually that number E we talked about a while back. The 2.718. So let's remind ourselves what that was. It was 2.71828. 1828 forever and ever. Okay. And remember, that's a number that always comes up with exponential growth. So if you see ln of 2, ln of 2 means that you're supposed to be finding the log base E of 2. Okay. Or it means what power do I need to raise E to give me an answer of 2? Now, why do I need a calculator for that? Do you know the answer to that? Like, I don't really know the answer to that, right? Because E is not a pleasant number, right? E is 2.718, blah, blah, blah. Okay. So we're going to need a button to talk about E because E is not a pleasant number. All right, so in the last, notice log of 100 meant 10 to what power gives you 100. Okay. So what if I ask you to evaluate natural log of 100? Like I said, I use a cursive / italics L for ln because it looks too much like a 1 if you don't. Okay, so let's talk about what this means. Okay, if it was log log, or it's also called the common log, it would be base 10. But what's the understood base always for ln? E. So it's e to the what equals 100. Okay. Notice that's probably not something I could do in my head, right? Because again, e is not a pleasant number. So we're going to use the calculator for it. So we're going to do natural log of 100 right under where we did log log of 100. And notice we're going to get that the answer for natural log of 100 is approximately 4.605. Okay. Note that if we wanted to, we could check our answer. In other words, we could actually do e to that power, and we should get right about 100. Okay. Now, why doesn't it equal exactly 100? Because 4.605 has been rounded already, right? So using the same calculator, you can do e to the power of 4.605. And you should get pretty close to 100, and notice we do, right? We get 99.98, so pretty close. Okay? But the answer is what I boxed in there. The answer is 4.61. So if you raise e to the 4.61 power, you will get about 100. All right, so what about this? And this is actually going to be common for us to get as we start solving these more and more. So the natural log of e. Okay, so let's talk about what that means. So what did we say the base already is for ln problems always? The base is e, right? So it means what do I need to raise that understood base of e to give me e? Well, that's kind of a goofy question, right? But the answer is 1, right? I need to raise e to the first power if I want to get back itself again. So what actually happens when you have natural log and e is they're actually opposites of each other. Natural log and e are, remember, inverses of each other. So more specifically, they're actually inverse operations. So kind of like addition and subtraction are opposites. Kind of like multiplication and division are opposites. ln and e are also opposites. And basically, they cancel each other out. I'm putting this in quotations because essentially they really don't cancel each other out. They just leave an answer of 1. Okay, and 1 times something doesn't do anything to it. So essentially they really do cancel each other out. So let's do a couple of problems. So let's do a part A and a part B for E. So let's say I asked you to evaluate the natural log of e to the 5th. And the natural log of e to the x squared plus 4 power. So we're doing these together because they're really, really similar. Okay, so let's talk about what this one means first. What does this one mean? What's the understood base for ln again, always? E, right? So what do I need to raise e to the power of to give me e to the 5th? Well, that's kind of a goofy question, right? So what power of e do I need to raise? What power of e do I need to be able to get e to the 5th? I need this to be a 5, so it matches that, right? And essentially what happens with my ln and my e then, essentially? They kind of cancel each other out, right? Leaving simply 5. Okay, so the same thing here. What's going to happen with my ln and the e since they're opposites? It's going to cancel, and it's just going to leave what? Whatever the exponent happened to be, right? Which in this case is x squared plus 4. So it works the other way too. And what I mean by that is you won't see this as often But if you had e raised to the natural log of 3 power, so in other words, the e function first, then followed by the ln, they still cancel each other out no matter what order it comes in. So what happens here? These cancel, and what does it leave then?
3.
Just 3. So just think of e's and ln's as opposites. Okay, they'll always cancel each other out. This is example 14. I don't know why I wrote 4. So let's do one more ln problem, and then we're going to remind ourselves about log instead. So there's a couple of ways to do this. One thing to note is that you can't cancel ln and e when it's in the fraction, or when it's in the bottom of the fraction. So maybe it would be better for us to think about this one as a rewrite step. So what do I need to raise e to the power of to give me 1 over e to the 16th? So don't make that harder than it needs to be, right? It's going to be 16, but what kind of 16 since it's a fraction? So what kind of 16 would it be since I have 1 over that? It'd be negative 16, right? So they still cancel each other out. We just note that the 16 is in the denominator or something like that. So it would be a negative there. Okay. Another way to rewrite this is you also could have rewritten it as the natural log of e to the negative 16th power if you wish. And then you could have just said, okay, now these cancel, and you get negative 16. Okay, regardless of how you think about it, the answer is still negative 16. All right, so let's switch back over to common log or just the log type log. So notice I'm asking you to evaluate log of 10 to the 2x power. Okay, so note I did not give you a base. So what's the understood log log base when I don't tell you?
100.
Well, no, that's not the understood base, right? The understood base is what? 10. So what do I need to raise 10 to the power of to give me an answer of 10 to the 2x power? So don't make that harder than it is, right? The 10's already matched. So what does the exponent need to match with over here? Like, what does the exponent need to be? 2x, so that it matches what we have over there, right? It's almost a goofy question. Like, what do I need to raise 10 to the power of to give me 10 to the 2x? Well, the answer is I need to make it a 2x so that it matches the right. So just like ln and e cancel each other out, log base 10 and 10 raised to a power are also inverses, and they also cancel each other out. So just like ln and e are opposites, log log and 10 to a power are also opposites. So if you're asked to find 10 raised to the log of 45 power, so before we do anything else, what's the understood base here? The understood base is what? If I don't tell you, right, what's the understood log base for log? 10. So notice this is 10 to a power and it's the log base 10, so what are these going to do with each other? They're going to cancel each other out, leaving only what number? 45. Okay, so it doesn't matter if the log is first or if the 10 to a power is first, just like with the e and the ln, they're actually going to cancel each other out.